This is lesson 10 in the physics unit, the last physics lesson of this COVID era, and we're going to talk about efficiency. And as an example of efficiency, we're going to take a look at this car, this really fast car. And what's making it move? Well, it has a fuel tank, and fuel is a type of potential energy. It's chemical potential energy. And that energy stored in the fuel is then converted in the engine and then used to propel the car forward. Okay? But not all of the energy that's in the fuel is converted or transferred into kinetic energy. What happens to the rest? Well, you know that engine is hot. You know the tires rubbing against the ground, that would be hot. So much of the energy that's stored in the fuel isn't just used to make the car move forward. It's also dispersed as heat. So we'd say that car is not transferring the potential energy stored in the fuel to kinetic energy of the car moving 100% efficiently, or at 100% efficiency. What we mean by efficiency is how much useful energy do you get from the energy you put in. So as a definition, we'd say efficiency equals the ratio of useful output energy to all of your total input energy. If you do that, you'll get a decimal that you'll want to multiply by 100% in order to get efficiency as a percentage. We talk about it as a percentage. We have to make sure that the units we use for output energy and input energy will be the same, and it should be. We'll use joules, maybe kilojoules if we need to. And let's go ahead and look at some examples for efficiency to get a better understanding of how to look at it and how to work out this equation. So this example, it's not in your textbook. I am using a different book here. I think it's more simplified examples. And it says you have a crane that's lifting a load of construction materials. So you have a crane. This is my drawing of a crane. And it's lifting a bunch of construction materials up to the second floor of a building. We're told that the crane does a certain amount of work to all that construction material in order to lift it up. It's doing this much joules of work as an input, while doing this many joules of useful work output in actually lifting the load. What is the percent efficiency of this crane? Well, we have a formula. Efficiency equals the useful output divided by the total input energies, and then you'll multiply by 100% in order to convert your decimal to a percentage. Now, one thing to note is efficiency, it will always be less than 100%. In the real world, we can never be 100% efficient with our machines, mostly because no matter what we do, some energy is dissipated as heat. So if you ever calculate efficiency and you get a number greater than 100%, then you know you're wrong. And what you're wrong in is probably flipping the output or the input, or mistaking the output for the input. So efficiency is always going to be less than 100%. If it's not, maybe what you think is the output is actually the input. So let's go fill in our numbers. Our output is the useful work done, which is this 8.0 times 10 to the 3, 8 times 10 to the 3 joules. And our total input energy is that 2.3 times 10 to the 4 joules. We'll get a decimal if we divide those two numbers. Then we multiply by 100 in order to convert to a percentage. So 8 times 10 to the 3 divided by 2.3 times 10 to the 4. Remember to use your E or EXP button on your calculator for that. That would equal 0.3478. You multiply by 100%. This becomes 34.78%. If we're looking at significant digits, there's 1, 2, 3 significant digits for input, 1, 2, 3 significant digits for output. So our final answer should have 3 significant digits. 34.8% is our efficiency of this crane. Next example, here we have an internal combustion engine with an efficiency of 15%. So we're given the efficiency, and it says it will do 3.2 times 10 to the 4 joules of useful work, which is your useful output work. Calculate the mechanical energy input that had to be supplied by the combustion of the fuel. So we're given efficiency, we're given the output, we want to calculate the input. Okay, we have our equation, efficiency equals output over input multiplied by 100%. We want to figure out what the input is. Now, what we need to do is, since input is on the bottom, we need to get it back up to the top line. And the way we can do that is by multiplying both sides by input. So we multiply by input, and we'll multiply by input on the other side as well. And as a result, you'll have efficiency multiplied by input. I'll use brackets to make it more clear. On the left side, on the right side, input on the top and bottom cancel out, and you have output times 100%. Your goal, remember, is still you want to get input by itself. How can we get input by itself? Well, it's being multiplied by efficiency, so divide both sides by efficiency. And then you should get your equation for input, which is output times 100% divided by the efficiency, and that would be your equation. Filling in the values up here, we'll have input equals the output, which we're told was 3.2 times 10 to the 4 joules, that we're going to multiply by 100%, and then we divide that by the efficiency, which is 15%. Plugging into the calculator, you should get 213,333 joules, but our rounding should be to 3 significant digits, 1, 2, 3. So what we should do is write this as 2.13 times 10 to the power of 1, 2, 3, 4, 5. 2.13 times 10 to the power of 5 joules would be the input energy that needed to be supplied to the engine. And last example, we have a pot of water that's being heated up. 2 times 10 to the 3 joules of heat was supplied by the stove. So the stove, so if you had a pot and it's on a stove, this red stuff is supposed to be fire, then the stove is giving the pot 2 times 10 to the 3 joules of heat. But how much heat is the water getting? It says only 5.0 times 10 to the 2 joules of heat is being gained by the water. And what's the whole point of putting the pot of water on the stove? It's to heat the water. So the 5 times 10 to the 2 joules of heat, that's your useful energy output, the useful energy. So if we're calculating efficiency of the stove, and efficiency is output over input times 100%. The output is 5 times 10 to the 2, whereas the input is 2 times 10 to the 3, and we multiply it by 100. If you happen to mix that up, if you happen to say this should be 2 times 10 to the 3 divided by 5 times 10 to the 2, you would actually, and multiply by 100, you would get a number greater than 100% efficiency. And that's one of the ways you would know that your calculation is incorrect. For the efficiency, the output always has to be less than the input, always has to be a smaller number than the input. Okay, let's plug that in the calculator, and that should be 25%, but we have 3 significant digits in our data, so we should write this as 25.0% efficiency. All right, that's it for physics. I'll give you some homework on this efficiency part, and then we'll have a quiz the next day, and then we'll start our climate unit. Thanks.